My name is Andrey Kuznetsov. I am the computer vision leader at Sber AI. And today I'm going to speak about our latest research in the field of diffusion-based text-to-image generation. It's Kandinsky 2.1. And I make excuses about my voice today, and I will have sometimes coughing, but I hope that the presentation will help me to cover all the topic that I wanted to share with you. So the content of my today's report consists of the following topics. Yeah. So we start with the task history. Then we proceed to description of diffusion process, how it works for those who maybe is not familiar with the details of diffusion-based image generation models. Then I will say a couple of words about existing diffusion models, and then proceed to Kandinsky 2.1 and existing achievements and experimental results that we already gained when estimated the quality of our model. So let's start with the task history. It is a common knowledge that classical C problems were usually always solved in one modality. So if we speak about segmentation, classification, object detection, and all other tasks, most of them are usually solved using one image modality. So we take an image data set, we take some labels, we take some segmentation marks, segmentation landmarks, and try to evaluate the model, try to train a model to solve some downstream task like classification of some object and so on. And everything was in the same pipeline, but in 2014, there was an immense boost in development of generative models. So generative adversarial networks appeared. And on the base of these types of networks, started to appear a lot of new applications. And by 2016, the main research is focused was focused only on the unimodal architectures, but from that time started to appear new types of models that use text descriptions to generate images. And the first mentions of such an application of generative adversarial networks were on ICML and on NIPC PS in 2016. And from that time, since 2017, no machine learning conference that has A or A star rating was not proceed without publication on the topic of image synthesis from text descriptions. So all the time, researchers tried to improve the quality of generative model and solve some specific problems of generations. So if we cover all this history in several main steps, and several main key points, then I would select the following one. 2016 is the start of generative adversarial text-to-image synthesis. If we cover and try to evaluate the citation quality and citations of citation statistics on Scopus, then we can see that this topic is covered by more than 600 citations. Then appeared attention guns. It's a new type of networks which used some attentional generative mechanism. At the same time, the attention is all you need appeared a famous paper about the attention mechanism of transformers. Then in 2019, another update of style gun appeared. It's stack gun networks, where several stacked generative adversarial networks were used to improve the quality. And 2021 was the main start of what we say now, text-to-image generation history. It's the most popular models, the most well-known that were developed by the company OpenAI. It's DALL-E and CLIP. And at the same time, the researchers from China developed their model CogView. So this was the start of the history, of the modern history of text-to-image generations. And here we can see a chart where the number of documents by years from 2016 to 2021, we can see that every year much more papers appear on the topic of text-to-image generation. So let's proceed to the diffusion process, which is the up-to-date, the state-of-the-art mechanism for text-to-image generation nowadays. So here are presented several approaches that are used for generating some content. Three of them are based on some latent space presentation, just for historical note. And the diffusion process is presented on the bottom of the slide. It is some iterative process that takes some input data and tries to make it noisy, and then tries to denoise it to get the data that was noised during this iterative process. And the history of this approach goes back to physics, and this is a good implementation of some multidiscipline research where machine learning and computer vision in company with physics presented a new approach for computer vision. Diffusion models are already, they already have some notion, have some naming that is usually used in most of the papers. This process is usually called the denoising diffusion probabilistic models. Actually, if we take all these four words from this name, we can see that we have some mechanism, some model, which is used to denoise some data using diffusion process. And this diffusion process is modeled and realized using some probabilistic laws, some probability laws. So this DDPM process can be divided into two main sub-processes. It's the forward diffusion and a reverse diffusion process. The forward diffusion process can be described as follows. So we have some data, some clean data that we want to generate in future. So we have some data set, but we see one sample over there. And the forward diffusion process means that every step of diffusion process is based on some additive noise generation. So every step adds additional noise, Gaussian noise, to the input clean data. At the final step of this forward diffusion process, we can find just clean Gaussian noise. So no structure, no information from initial image is presented. And the most interesting process here, which leads to generation results, is the reverse denoising process, which is already named as generative process. And this is the process that is usually trained during denoising-based, diffusion-based architectures training. If we go into details of probability basics of this approach, so we can see that every step in our iterative diffusion process, forward diffusion process, is based, as I already said, on adding some additional additive Gaussian noise. And this noise is described with mean and standard deviation. It's common knowledge. The idea is that every step is connected with the previous one. So we have some probability law, and we try to estimate the parameters of our step, not only from the previous one, but from the zero one. So the idea is to find out the law or some equation that can combine and that can give us information how to estimate the information at some step using not all the previous steps, but only the zero one. And this is described by this equation. So here we can see the multiplication of several probabilities. And the idea of the why diffusion is leading to some generation is that we do not know the inverse information about the probability. So we cannot find out just using equations, simple equations, how to estimate the process in the reverse direction. So this is the idea where conditional probabilities help us and base general knowledge of probability distributions and the laws of multiplication of probabilities leads to better details and understanding how it works. Further, there are several slides that describe the process in details. I'm sure that most of listeners who are familiar with most of you, I think, are familiar with probabilities and the laws of probabilities and the theory of probabilities. So I think that if you go into details, you can understand everything from these slides. So the idea is to estimate the diffuse data distribution using some joint probability distribution. The diffusion kernel is just something that helps us to estimate the probability from the zero step, the conditional probability. Going further, we come to some data generation through the denoising process, and we see that when we go in the inverse step, we try to find out how we can create a distribution from normal distribution to the initial one. So the initial one is unknown, the initial data, and then we go back to the data that we want to estimate. And this is usually approximated by some normal distribution with the standard deviation beta, which is usually extremely small and takes values from 0 to 1. The reverse denosing process is presented here. The trainable part is the standard deviation, and the mean part actually that we want to estimate to find out how good we extract the noise from every step when we go in the reverse direction. So here at every step, we estimate how much noise is deleted, is removed from the image. And using the final metric, we train the model to evaluate the images from the noise, from the initial normal noise distribution. Here are some information about the noising, the model training, where the loss function is described. It is actually a variational upper bound loss function that is calculated using Kullback-Leibler divergence for two distributions. The initial one, which is the P1, it is the actually ground truth distribution of the data, and information about the predicted probability condition by x0. And here are information about the steps. So we estimate as a hyperparameter of our network the number of steps and try to evaluate how good is our reverse generating process, changing the number of steps of diffusion, which leads to better or worse generation as a result. So this is some pseudocode about the training and the inference step of our generation. So after the evaluating of the training phase, we estimate these parameters of the distribution and then of the normal distribution. It is presented on the slide, and then use the parameter alpha for generating at the inference step the new samples for the distribution. And actually here we can see some sigma that helps us to change the information that we want to generate. So adding some noise to the samples. So speaking about the existing models, I think you're familiar with these models because they are quite well known, and a lot of information was presented last year in different resources. It's DALI2, which is a clean diffusion-based process, which has some unclip procedure, which has some prior model that is used to generate images, and some decoder part, which makes the image as we can see it. So it is pixel-based diffusion. It means that we work with images, just with images, not with some of their representations. Imagen is the development of Google research, and it is presented as a sequential procedure of super resolution networks, which actually improves in quality, and the quality of Imagen, according to their paper, is the best one in terms of the main metric FID, Fresnel exceptions distance. However, it is quite difficult in computations. It is a computational complex model because every step of super resolution is quite difficult, and the generating process should be really low. The computation complexity will be high, and the generation time will be also high, because every step is based on some diffusion model, and every model has its number of samplers, steps, and so on. And when we extend the resolution, every step takes much time if we would implement it as is. So another approach appeared last year. It is based on the latent diffusion process. It means that now we do not work with images itself. We work with their representation in the latent space. So here we can take not the image of a man, but the latent space presentation of this image. So we work with vectors that are much smaller in size, and we can get much more information from the images. So let's proceed to Kandinsky 2.1 architecture, but I will start with Kandinsky 2.0, a couple a couple of words about this model. So the idea of 2.0 architecture was to use several text encoders to create the vector in the latent space that we want to to proceed through diffusion process and receive some latent representation of the image. So we took two text encoders. This was done in order to create a multilingual architecture. This was a very interesting experiment. Two encoders were concatenated, and after layer norming, proceed to the diffusion UNet architecture. UNet architecture was trained on practically 1 billion set of pairs, text and image. And after that, we generated latent space representation images, and using the autoencoder that was used from Kandinsky previous versions, it's just VQGAN architecture. We generated images by the text prompting. So it was a latent diffusion-based architecture. The generations were quite good, especially if we use cherry picking, but we wanted to provide a better model. So we started research in changing the architecture and adding some image prior model to embed the quality enhancement from DALL-E 2 approach, because it was, and it is, from my point of view, one of the best ideas, because image prior gives a lot of improvement to the quality, as you can see. So here is presented some information about the released version of Kandinsky 2.1. It has 3.3 billion parameters. It is already, it is also a latent diffusion model, and we released it actually 2 weeks ago. So here you can see the difference in quality. The difference in quality of generating stickers or some images for different social networks. What is the idea in our architecture? Here you can see a slide on the left side. There are 3 columns. I will describe them separately. The first one is the clip training. Clip-based training is training some diffusion mapping, which is an image prior model, which is inside is a transformer, which is used to find out the corresponding quality, the corresponding features between text embeddings and image embeddings. So here we take the data set of pairs of text and images in Russian and train using clip text encoder and clip image encoder some diffusion mapping. What this information gives us. So after the training process, we have this red block, which is called diffusion mapping, which is an image prior model. Further, when we take the second row, the second column, here is the text to image model itself. How it works. In basic, we take the text information, we use some encoder to create a vector representation of this text, and usually it goes to latent diffusion as it was in Kandinsky 2.0. It goes to the green block, which is just a UNet diffusion model, which then generates us some latent representation of the image, and we generate it. What we do in this architecture, we use this diffusion mapping, taking as input the information of about the vector representation of the text, use diffusion mapping to find out the corresponding image vector, which is a clip image encoder or representation of the image, concat this information and push it to latent diffusion UNet that was already trained on the previous step. So here we didn't train it from scratch. We used it from Kandinsky 2.0, just fine-tuned it with the new image decoder. And the next main step of this architecture is this image autoencoder. It is a very interesting, however simple architecture. You can find it by the name of this architecture, and actually it gives much more in terms of quality, much more results in terms of quality. And the last column is just one of function of one feature of our model that we can take not only text as input, but for example, to images. We can encode it with clip image encoder, can get this information, push it to latent diffusion, and receive some which we call mixing images. It's a very popular feature of our Telegram bot. A lot of people use it just to mix several images in some personal, for some personal ideas. Speaking about the architecture, I already said that it contains 3.3 billion parameters, and here we can see the information about different different parts of the model. So further, I will show the results of generation by different features of our model. It's text-to-image generation. Here you can see the generated images. The results of mixing, when we take some original image, some style image, and generate images with some styling. And image and text fusion. So we can take image, we can take some additional text, and try to interpret this image according to the text. Image variations. This means that we take as input an image and try to generate using diffusion some similar images from the latent space. In painting and outpainting features are presented on the website fusionbrain.ai. It is something like an image editor where you can visit, generate images, or even upload your image just to make some changes. So here you can see that we take initial image, using eraser, erase some part of the image, and then generate, for example, a car by description. And the outpainting is the same. Speaking about experiments, we calculated the Fréchet substance distance of our model. It's the basic metric for estimating the quality of the model. Because our model works in several languages, we use it in English just to compare with existing models. And, according to the experiments, by the moment we have the third place in the list of existing models which publish their results papers. To test the model, you can take one of the four resources. It's Telegram bot, the website fusionbrain.ai, the website udali.ru, and the feature of Salute in Salute Sber devices. So here are some results, screenshots from these resources. By the 20th of April, I updated the statistics yesterday. We have actually nearly 3 million unique users. The number of queries in all the resources is nearly 28 millions. It is a very big amount of queries, and the first days of our release were very difficult in terms of quality of the backend server. Speaking about the detailed statistics from the 4th of April till 20th of April, here you can see how it grew by the 9th of April, and then starting to fall down a little bit. So this is the result by yesterday. Speaking about the queries, most of them are about descriptions of people and animals, about some places and different objects. It's the orange one. Styling the images is the green one. Questions about and queries about generating some Russian styling, for example, some Russian objects or something that is connected with Russia. Some abstractions it's a very big amount of queries. And then goes some famous people, logos, and so on. Speaking about the achievements, we can see that in terms of comparison by different queries with Yandex Shedevrum, seems that our model reached better results, and in terms of quality, understanding the long, difficult queries. So the last one is the famous Izbushka na kurich noshkach. It's a house on chicken legs. And here you can see the samples from Shedevrum and our result. The Russian community feedback was very interesting. A lot of bloggers and famous people tried the model and published the results in their personal channels. It was very interesting, and very good results were shown. The international community feedback was also good. It's a Reddit branch of discussing the model. The Hugging Face CTO described our model, and a very good overview of medium.com was also presented. Another information about international community feedback, comparison with Midjourney, especially in terms of its paid functionality from some moment, the beginning of the April. The paper on Haber took the second place in the best papers of the 4th of April, and now it takes the 4th place in the best papers of the month. Speaking about the statistics of the GitHub repo, we have 1.5 thousand stars, and the statistics of cloning is also quite good in comparison with other our repos. Also, the model took the 4th place in GitHub trends on the day of start, or the 5th of April, something like this. The Hugging Face also has the implementation and the grad.io implementation of the model. Different machine learning platforms or image processing platforms for fast model embedding used our model to show the results of and the quality of the model, and already some websites like fuups.ai, they also have a marketplace where you can find the images generated by our model that people generate and try to sell. This is the statistics about the audience. Some list of opportunities for creative industry. We just thought about marketing visuals, logos and icons, images for presentations, some simplifications of images for different marketing solutions, and so on. So a lot of ideas may appear when using such models, especially when they are free of charge to use. So in conclusion, I would like to say a couple of words about the popularity of the text-to-image synthesis. Here we can see a lot of applications, a lot of solutions that use inside the generating models. However, big image stock companies, they embed information about using text-to-image generation models just to extend the number of users and to add additional and to add some functions that are new and very popular now. So if you will have any questions, you can ask me in Telegram directly, or you can read the channel on Telegram where I describe some modern architectures or post some news about our research. Thank you very much.
Andrey, thank you very much. And we have time for questions. So please, if you have, raise your hand. Okay, it's fine. I have many. So Okay, let's start with more technical, maybe about how you have evaluated the model. So you said that you used Fresh score, but about the model evaluation. So you used Fresh score feed. Yeah, here. Have you also used human evaluation during the fine-tuning and development?
At this experiment, we didn't have resources for this. We tried human evaluation on when developed Kandinsky 1.0 architecture, but at the moment we didn't have just resources for estimating using human evaluation. But yes, this is a good idea. We obviously will do this.
Okay, and actually you solve lots of problems. So let's separate, for instance, processing queries in English and in Russian, and also mixing images. So what tasks are solved better? What tasks are solved worse?
Most of the tasks are solved better in English in terms of generation, because the clip that we used is the English clip version trained by OpenAI, and actually the clip image encoder is the VITL architecture, and the text encoder is also taken from there. So this is the idea why this improved the quality, but other languages are used through translation right now. Speaking about the image fusion, a lot of experiments should be done when you try to mix several images, because when you use a bot in Telegram, you have the ability to set the mixing parameters. Yeah, so you can set some mixing coefficients just to find out which is better, and sometimes it is taken in the second digit or even in the third digit just to find out the good mixing. For example, you want to mix Cheburashka with the crocodile, and you start to combine these values, these weights, and it is quite difficult. It is not a simple operation just to find a good result. So I think generation is the best one in terms of quality for now. But other features are also interesting, but would take more time from you to reach a good result.
Mm-hmm. Okay, thank you. My next question is about prompt and how do you censor it? Because obviously you do not generate porn images or some violence images. Is this only on prompt analysis, or you also try somehow to see what's generated?
We use only prompting analysis just to extract some words that are toxic, some phrases that are toxic, and try to filter them.
And I don't know if you can provide these statistics, but among the prompts, how many are censored out?
We didn't calculate it because we did several experiments with filters. We added them at the moment, at the start. They gave us a big percent of false positives, and we removed the filters. And several days ago, we again added them, the new one, the updated version of filtering to the Telegram bot. And most of the resources, or most of the training was pointed on child porno and just pornography, and we tried to remove such queries. But I think that we will calculate some statistics and show some a bit later. But I think at the moment we just do not have a lot of information about this. But yes,
okay.
this is a good point.
Okay, thank you. So we have a question from the audience.
First of all, thank you for the presentation. And I have a question about other metrics that you used or not used for the training. For example, the correspondence between the text initial prompt and the generated image. How do you manage to measure it and compare it to the different other papers?
We will publish this information in the paper that we are writing now. I didn't add it there because it was not updated at the moment. But yes, clip is a good measure to evaluate the quality of the correspondence of and similarity of image and text. We calculated in previous models, but by the moment only have FID experiments.
Okay, thank you. And what's going to be in Kandinsky 2.2 or 3.0?
Actually, there will be announced two different models. About 3.0, I will not cover the details, but about 2.2, I can say that we would like to add in the nearest time the larger resolution. Now it generates only 768 pixels on both sides, and to add different aspect ratios, not only for just not to generate only square images, but also some rectangular.
Thank you. And about the measuring of the performance of the image mixing, how is it evaluated?
Actually, there is no metric, I do not know, to measure the quality of image mixing.
So you mean objective metric, and you just used it like visual comparisons?
Maybe, yes, this is a good point, but we have to collect specific set for this, just to compare object in terms of objects, to compare the generation and mixing of some images.
Thank you.
Thank you.
Thank you. Any more questions from the audience? We have one quick. So, okay, I would ask, what was the main challenge? Like, what was the most troublesome thing with training Kandinsky 2.1?
The selecting and embedding the image prior was very interesting when we concatenated the vectors to evaluate the final result. And different experiments with freezing the initial latent-based diffusion model for image generation. And it was a very interesting result that it was trained mainly with Vikagan encoder previous version. And when we added the MOVQ, the new encoder of images, it was fine-tuned quite fast. So it means that changing the latent space for images is not a very complex computational operation. And there were, we used one or two GPUs, A100 to do this. It was a very interesting effect. The changing the image encoder is not complex operation.
Okay, so thank you very much, and thank you very much for the talk. Actually, I just want to express that Kandinsky is surprisingly good, and also I was really surprised by how many people got using it so quickly. So my congratulations. I think it's a really big success, and thank you very much for the talk. Thank
you very much. If there are any questions, though, you can write me. I will with pleasure answer you.